Hi everyone, my name is Jorge Ganzo. I'm a student at the Polytechnic University of Valencia, and in this video I'll introduce our work, Segmentation-Free Streaming Machine Translation. First, let's define a streaming machine translation model. We consider this as a model that is able to translate an unbounded input text stream in real time, typically as a part of a cascaded system with text coming from an ASR model. Usually, empty models are trained on distinct sentence-level segments and assume full vision over the input. But here, the model gets increasing partial input with each new source token from the incoming source text stream. Previous systems use an external segmentation model to decide whether to split the stream into chunks for the empty system. This is the standard approach. An evaluation is typically done with respect to a given goal reference segmentation of a dataset. However, there are some problems with this approach. First of all, there is a context loss due to segmentation-based models typically translating the detected units in isolation, not using the information outside their windows and losing on crucial contextual information. At the same time, the segmenter may introduce segmentation errors for which the translation quality can be heavily affected, alongside additional latency and computational costs. Furthermore, models which rely on external segmenters typically use only information from the source stream, missing on potential target side information for which the translation model may benefit performance. As such, we asked the following. How do we build a true long-form streaming model that uses previous stream context and doesn't rely on an external segmenter? Some previous works address this question. Schneider and Weibull trained a transformer XL to predict and accumulate probabilities holding generation until a threshold was reached using a rolling window of tokens. Alongside this, Secunta and et al. Used a variable size sliding window when translating each new token, each new input, and merging outputs to get the final translation. Our solution consists of the following. To train the translation model to decide when to segment the input stream itself. We introduce a special separator token, SEP, in the target stream during training, similar to offline document-level machine translation models. These tokens act as sentinels, helping the model track source-to-target segments and differentiate them between already translated chunks and the current active chunk, allowing the oldest pairs to be safely discarded. Our memory mechanism uses a log linear feature function model to decide alignments when the SEP token is generated. This gives out a probability distribution for the last word of the active chunk to be moved to the history buffer. In essence, we can get the chosen A position for this last word of the source, given the maximum of the weighted sum of all features. This method is flexible and the corresponding lambda weights are easily learnable over a small training set. Some important features that we found out to work well in this work were the use of a reverse translation model and a normal distribution conditioned by a linear regression model dependent on the target length. For a better illustration of the mechanism, let us imagine translating an English stream to Spanish at time I, with maximum of one history chunk. Our mechanism has identified reduced harmful emissions with the Spanish output and an active chunk of partial input. At the next time step, the model reads a new word, it, and writes the token SEP to the target stream. Then, our log linear model identifies the best position for the active chunk, which corresponds to that of the token DAT, moving the chunk into the memory buffer. Finally, since we have limited ourselves to only have one chunk of memory, we eliminate our oldest pair in this case. For our experiments, we focus on English, German, and Spanish and French, and we obtain our data from outputs and audio SLT for both machine and speech translation corpora, ranging from 95 to 320 million sentence pairs, depending on the language direction. Normalizing and lowercasing our source data to assume the case where input is coming from a typical ASR system. Then, to teach the model to produce SEP and use additional context, we augment the typical prefix paradigm for streaming machine translation. And inspired by document-level empty, we concatenate previous sentences delimited with SEP at various rates up to a limit for corpora where document-level information is present. In case of our models, we train bidirectional encoder-decoder transformers in their big configuration, using weight K for easiness of experimentation. We also make use of speculative beam search and limited ourselves to 50 words in our memory buffers, as we found out to be a good trade-off between latency and quality. We additionally train two models which represent state-of-the-art solutions in both the segmented and streaming setups to serve as baselines. We follow previous work for evaluation on segmented corpora and concatenate all sentences of a document when translating, simulating an increasing input stream. We then realign document-level hypotheses to sentence-level golden references using a Levenstein-based aligner and calculate quality metrics. We additionally make use of modified stream-level latency metrics to properly consider interphrase delays, which are often ignored in typical evaluation given a golden segmentation. We also report neural quality metrics apart from the classic BLE, and evaluation is done on standard HT datasets benchmarks, Europal ST and MAST. As for results, we first present our findings on feature exploration. At the left, we can see how a combination of our previously mentioned features improved greatly with respect to sliding window naive approach in both latency and quality metrics. While at the right, the presented log-scale histogram shows how our approach significantly reduces overgeneration and undergeneration. It's reflected by the frequency of length differences of outputs with respect to golden segmentation. As for general results, we report our final findings on English-German in Europal ST, and find that our model achieves the best result across all tested latencies with respect to baselines, closely matching an Oracle model with the golden segmentation. We also see how results on average lagging and BLE are also consistent when evaluating with the computational aware translation lag metric and the neural blurred quality metric. As for MAST and other language pairs, we also find similar results with our model coming on top for the majority of cases. With this, we have reached the end of our presentation. The following is the list of related work which have been mentioned in this presentation. For additional results and discussion on streaming machine translation, join us at our oral presentation at ACL 2024. Thanks for watching.